I'm lucky, so we'll start again. Hello, everybody, and good afternoon, and welcome to yes, and welcome to this CIGRE Ireland webinar. This is going to be the first of a series of events that we're going to run through the year and focus on sharing the experience and the activities of the various study committees. We're starting this series of events today with Study Committee C4, Power System Technical Performance. My name is Marta Val Escudero, and I am a member of the Irish National Committee and also member of Study Committee C4. Today, I will be giving you an overview of what the Study Committee C4 is all about, what we do, and what type of outcomes are available to you as members. And that will be followed by a presentation given by Papilla Dacharay on one of the on our working groups, which concentrates on the impact of high penetration of inverter-based generation on system inertia. This is a topic of great interest these days on the basis of integration of renewable generation and the transitions toward decarbonization. So Papilla's presentation is about 60 minutes long, so we'll be having a break halfway through her presentation. And at the end of the session, at the end of both presentations, we'll have a Q&A session. So please send your questions through the Slido platform and the password that you have there on the screen, CIGRE. So before I start talking about the study committee, I just want to give a few words about what CIGRE is for those that may be listening and they're not members or they're not very familiar with the objective of CIGRE. So CIGRE is basically a global community whose objective is to facilitate a collaborative development and sharing of power system expertise. It's not a profit organization. All our membership fees go to running the organization and supporting knowledge dissemination events. And CIGRE was kind of established in Paris in 1921, exactly 100 years ago. So this is a very big year for us. As I said, it's a global organization. We have 59 national committees, 15,000 members from over 90 countries, and over 1,200 organizations are participating in one form or the other. So for more information, I will encourage you to go and visit our website where you will find all details there. So CIGRE organizes this knowledge management into 4 main areas: equipment, technologies, systems, and new materials and IT. And within each of those groups, there is a subdivision of more specialized topics, and each of those specialized topics are dealt by a study committee. So there are in total 16 study committees in CIGRE, and CIGRE Ireland has representation in 14 of them. And I have shown here on the slide on the screen the names of the representatives for each of the study committees, so if you want to kind of reach out to any of them. But today we are concentrating on C4, Power System Technical Performance, and as I said, I am the representative on this committee. So what is C4 all about? So this study committee is probably the most diverse of all the 16 study committees. It primarily deals with methods and tools for analysis related to the technical performance of power systems, with particular reference to dynamic and transient conditions and the interactions between the different network components. So this kind of scope covers a wide range of phenomena and time range, and we have grouped all these different topics into 5 main areas, which are power quality, electromagnetic compatibility, insulation coordination, lining, and power system dynamics and numerical analysis. This picture that you have on the screen here summarizes very nicely what the scope of the study committee is. As you can see, we covered a wide range of time frames going from nanoseconds to hours, and which will kind of reflect very fast tranches like lightning strikes and GIS switching towards the kind of slower events like long-term stability or unit dispatch and everything in between. And this very wide range of phenomena that is analyzed within the study committee, it requires different methods. Unfortunately, there is no kind of one tool, one model, one method of analysis that deals with all these different phenomena. And it's very important that we understand the causes and effects of each of these individual phenomena, and that they're properly analyzed and they're properly managed in order to kind of guarantee secure operation of the power systems. So this is kind of covered through the study committee, and one of the main kind of outcomes that we are producing is guideline documents that help the user, help the engineer when it's facing with one of those situations, how to better approach it, what is best industry practice. So that's kind of one of the main deliverables, the main kind of contribution from this study committee. This is particularly important now that we are kind of undergoing a significant transition in the power system in this industry. We're moving from a traditional world dominated by synchronous machines, thermal plant, towards a power system that is dominated and mostly by renewable generation, variable renewable generation that is interfaced normally via power electronic converters. So these two different technologies behave differently. They have different capabilities, they have different responses to events, and it's important that we understand both responses, and that we can anticipate any potential risk, any potential kind of interactions between these devices and the system, or, as I said, risks to secure operations. So we can analyze it, we can understand it, and we can predict it and manage it accordingly. So there's very kind of high interest in the industry, driven by the high penetration of power electronic devices these days, and there is a lot of work going on in the study committee to understand the phenomena and to kind of identify the best methods of analysis, the best models, the best tools to address this. How does the study committee carry out its duties? So we have the structure that you have on a screen. We have a chair and a secretary, and then 45 members representing 42 countries. The study committee is supported by 3 advisory groups. We have the strategic direction advisory group with liaisons with IEC and IEEE. We have the customers advisory group, and we also have the tutorials and conference advisory group that I have the privilege to lead. And the engine underneath all of this, the real kind of work is carried out in the working groups. We have currently approximately 33 active working groups, and I said approximately because this is a dynamic number depending on the working groups that finish their tasks and are dismantled, and new working groups that are being set up. So last time I checked, it was around 33. What's interesting here to mention is the division in between the different kind of areas of a study. So the dominant number is on the dynamic models and tools, and that again reflects what I just discussed earlier. That is the increasing need in the industry to understand the challenges and the methods of analysis for these new technologies that are connecting to the system. And we need to kind of understand how to predict any potential risk and how to manage them. So many of the working groups here are addressing those issues and new forms of instability, etc. And then we have the traditional power quality, electromagnetic compatibility, etc. I'm not going to discuss all those working groups in detail. I will refer you to the website where you can find all the details. But I just want to highlight now the working groups where we have Irish representation. So out of the 33 active working groups, Ireland has representation in 17 of those, which for a small country like Ireland, this is a massive achievement. And I want to kind of thank all these experts that are dedicating their time and sharing their experience. I want to kind of thank them and applaud their contribution, and also encourage other members to follow lead and kind of put themselves forward and participate in more working groups that will be forming in the coming future. Many questions that I receive regularly is about how to participate in new working groups. So the responsibility to nominate experts to join working groups resides within the national committees, and each national committee may have their own practices. So what I'm saying here, it only applies to members in Ireland. Other kind of people listening from abroad, please check with your national committee. So in Ireland, we normally circulate an email like the one that you see on a screen, and you have their instructions. You have links to the terms of reference, and you have timelines on when are we expecting nominations. So if please keep an eye on these emails, and if the topic is of your interest, if it's in relation to your area of expertise, or you have kind of a personal interest, please kind of reach out and put yourself forward, and we'll consider your nomination. Now, in relation to kind of members that work under ESB and ERGRID, please do so via your company representatives, because there is a need for coordination of nomination in those organizations. So in ESB, please contact Robert Donaghy, and in ERGRID, please contact myself. So the main outcome of the study committees is the production of technical brochures. These are very kind of comprehensive documents that summarize the work carried out by the group of experts, taking considerations from expertise from all different parts of the world. And it provides recommendations, it provides best industry practice, etc., on a particular topic of subject of the study committee. So these documents, as I said, they are very comprehensive, and some of them go into a huge level of technical detail. They're very good reference books in your desk, and they go through a very thorough peer review to ensure the integrity of their contents and the accuracy on the contents. So I have just kind of shortlisted here a few of the technical brochures that have been published in the past couple of years. Another publication produced by the study committee are reference papers, and these are shorter documents, no more than 10 pages, and they're written in plain language, and they are intended to reach a much wider audience, not so technical, not so specialized, and they're intended to explain in plain language some topics of emerging interest for the industry, and the intention is to provide the sufficient information to kind of assist on general discussions and to provide us those bases for informed decisions. So I have shortlisted here 3, but there are many others that you can find in the science and engineering journal. So the first one that I shortlisted is about the effects of increasing power electronics in power system stability. That was published back in 2018. Then in 2020, we published another one dealing with the modeling techniques and simulation tools, just looking into the limitations of traditional models and traditional methods and tools of analysis, and the need for a certain level of additional details for certain type of events. And the last one that has just been published this month is about system strength. Is what do we understand with when we talk about system strength, what are the implications of reduced system strength? How does it materialize in the system? How different kind of countries are managing this issue of system strength? What technologies are out there to help the operators to manage system strength, pros and cons, etc. So it's a very well written paper, and I encourage people kind of to download the latest edition of the Science and Engineering Journal, where you can find this reference paper and many other papers of great interest. Another outcome of the study committee is the organization of tutorials. So those are typically delivered at CIGRE physical events like symposiums, conference, etc. And they just provide a very kind of comprehensive overview of what the technical brochures are in a particular topic. We also organize webinars, and this is just very similar to the tutorial, but based on online, and they're getting very popular, especially now with lockdown. But I think that they're here to stay. We're going to see more and more of those events because of the obvious benefits and public interest on them. And all of this information, all of the outcomes of the study committees are available on the CIGRE online library. Even the webinars, they are recorded and you can access them later on the esigre.org. So I encourage people to go and visit and use it as much as possible as a reference point and a source of information for your day-to-day work. So this is kind of in a nutshell a brief overview of what Study Committee C4 does. If you need more information, you'll find lots of information under the website that you have on a screen. And if you have more questions, please don't hesitate to contact me. My details are there. And also, if you have suggestions on what the Study Committee should be looking at, emerging issues for the industry, please let me know. Or if you want to get involved, I'll be very, very happy to get a new pair of hands. So please reach out to me. And again, for today, if you have any questions, just please send them to the Slido platform, and we'll address them at the end of the session after Papilla's presentation. So for now, I just want to give you a couple of announcements very, very quickly. The first one is about the call for papers for next year's CIGRE Paris session. So the call for papers is open, and you have the details on the website. Please have a look, and if you're interested, just submit a synopsis of no more than 500 words by the end of March, and please send the synopsis to myself and copy Marniden, our secretary, on that communication. And the next announcement that I want to make is about the Next Generation Network. They're kind of holding the AGM on the 10th of March at 3 p.m. It will be hosted under Zoom, and please register in advance on the details that would have been circulated already. I just want to encourage new members, please get involved, and especially the ladies. Girls, please, we need more female voices in this industry, so please step up and get involved. And please, everybody, just if you have any questions about the NGN, please contact Jason. His contact details are there on the screen. And now I'm just going to pass you, I'm going to leave you with Papilla. Just before I want to introduce her, Papilla is a senior engineer at EPRI, and she's investigating transmission system reliability issues with high penetration of renewables. She received her PhD from the University of Manchester in 2018 for her work in novel mitigation solutions for subsynchronous oscillations. And while she was in the UK, she was very involved in the NGN in CIGRE UK. And when she moved to Ireland in 2018, she established the Irish NGN network here in CIGRE Ireland, and she was the chair of the Irish National the NGN. Also, she was a member of the Irish National Committee, and we're very, very grateful to her for all the contributions that she made to the National Committee. She's currently the secretary of the Joint Working Group C2, C441, and she's going to give you an overview of what the work of that committee is carried out. So, Papilla, I leave it.
Thanks a million for that introduction, Marta, and also thank you for inviting me over to give me an opportunity to discuss what we have been doing as part of the joint working group that you just mentioned. Before I move forward, can you hear me all right?
Yes.
Thank you. So, like Marta mentioned before, we plan to have a 1 hour long discussion on the various aspects of the technical brochure that I've basically partitioned into 3. Our technical brochure in total has 9 chapters, and the way we have broken it down would be, in part 1, we would discuss the basic motivation, introduction, and background of the work that we achieved under this particular joint working group. Certain definitions that we want to standardize for the industry, and a survey response from a number of utilities that we wanted to gather more information from. In the second portion, we'll discuss the particular challenges that you may face with low inertia systems with high inverter-based resource penetration. What sort of capabilities are required? What sort of capabilities do exist? And how do you discuss when it comes to inverter-based controls? In the last portion, based on the various challenges and capability requirements, we'll discuss how actual utilities perform system studies, in particular future system studies, to ascertain either inertia shortfalls or what sort of frequency control requirements will come up, what sort of system services are currently in place, and the policies. So that's, and follow it up with a conclusion. Before we move any further, I'd like to acknowledge our convener, Mpeli Ramkanya, who has been very kind to allow us to discuss and present all the findings from our joint working group with you all. Also, some of the chapter leads that I've mentioned here who have contributed in making the slides that have also been shared as part of the official tutorial that we presented as part of the working group. With those, let's dive into it. So first off, the objective and the scope of the joint working group itself. The idea was to advise and formulate the philosophies for system operators around the world in order to prepare for the ongoing energy transition, the transition to higher renewable penetration, and the challenges associated with it, particularly in light of displacement of synchronous generation and physical inertia, and the challenges that come with it. The key scope areas, as I already outlined before, is to review and consolidate the challenges faced by various participating utilities across the world, understand best practices, codes, and policies that are currently in place, or where are there any gaps, operational measures to determine inertia requirements, and we'll discuss more of those as we move forward, and how to quantify reserve requirements and any mitigation methods and so on. So with that understanding, we approached our various participants, and what I wanted to capture here was to just look at the motivation coming from different countries on why they want to look or participate into the inertia challenges and why are they looking at it at all. So more or less the motivation is coming from renewable energy targets. I have put on the screen 4 example cases where, for example, in terms of looking at it from Eskom in South Africa, they are projecting an increase in PV and wind installation capacity on their system to the tune of, let's say, 10 to 20%. And they want to do the studies to understand the technical impact that they will have at the moment with, let's say, 60% instantaneous penetration to as they transition forward. To the right, air grid, big motivation is their goal on 2030 to deliver 70% of the electrical energy from renewable resources, which would require an anticipated real-time penetration in excess of 90%. So really moving forward with that target in mind, there's a big motivation to try and look at the challenges. Also, the other notable point would be the ROC-off concerns that they do have, and they are moving from their existing limit of 0.5 hertz per second, transitioning to 1 hertz per second, and we'll discuss the details more as we move forward. But there are notable changes that they are seeing in their grid and moving forward, so they want to plan for those. Similarly, looking at it from Texas, USA's perspective, their biggest motivation was they currently have a critical inertia floor. They are looking at increasing the penetration again, and they want to understand where they are now. Do they need to prepare further for that transition or not? AMO, as an example, one big motivator was the inertia shortfall studies that they did and identified that in South Australia, there was actually some shortfall that was identified. And they are constantly trying to see, okay, do we need to define secure operating inertia levels, which they have currently in islanded mode? Does that need to be updated as we move towards a renewable future? So different system operators around the world, they shared the concerns across the board, and they all come together as part of this. They came together as part of this study committee, and we tried to put together all the learnings and the findings, and so that the wider community can get a peek into those ideas. So with that, I think we are ready to dive into the first part of the talk itself. I would also again iterate, please feel free to drop your questions on Slido as and when they come up, and then Marta and us, we will come back to them either through the course of the presentation or towards the very end. But just so you remember, please drop them down. Okay, so the first thing that we did was at the very beginning, we dedicated a chapter which looked at the background of the concept of physical inertia and tried to standardize what we mean by inertia, emulated inertia, fast frequency response, and so on, and how each one of them ties together. For the audience who may not be very familiar with the concept, of course, like I said, reduction of power system inertia is directly tied to the displacement of conventional generation coming from the various renewable energy targets that have been coming from the governments around the world, be it Europe or Australia or otherwise. And what the displacement of that synchronous generation does, on top of a lot of other impacts, it causes a lack of or loss of physical inertia. Physical inertia is basically the mass rotating behind in the conventional generation, which stores kinetic energy. So whenever the system sees a change, either a change in load or any big disturbance, that big rotating mass slows down, releases that kinetic energy, and it's all physically interrelated in an AC interconnected system. So if you have more mass, of course, the rate of change is lower. If you have less mass, the rate of change is higher. When the rate of change is higher and the system is moving faster, of course, there are concerns around whether or not the existing frequency control that I have in my system, is that enough to be able to stop my system at a state and bring it back to a stable equilibrium, or do I have to look at it and come up with more efficient solutions? Moving and like I said, that comes from the changing resource mix. A couple of examples, obviously, the conventional synchronous inertia, be it coal or gas, is now getting replaced by wind, solar PV, BESS, and various other technologies, which are all inverter based. And on one hand, it's decoupling that physical system from by putting a decoupled power electronic interface. So on one hand, it is basically reducing the system inertia where it's displacing the physical units, but also bringing with it a lot of capability, which are primarily given by the controls that you can manipulate to give what you need. So in one way, the problem and the solution are coming kind of hand in hand, and there is a need to streamline and modify our policies so that we can make the most of this transition. So like I mentioned before, the faster the system moves, the higher the rate of change. That is what has been shown on the figure on the right, on your right-hand side of the system. Basically, what you see are 3 frequency traces and their relative impacts as the inertia decreases. And you can see that the rate of change is much, much higher. So inertia basically plays a key role in that initial rate of change of frequency. Now, once we have learned about inertia, and I also loosely mentioned other terms which were related to frequency control. So these 2 things are tied together. Because on one hand, you have a disturbance, and what you see on that light opaque box, which is transparent, is the very fast transient immediately following a disturbance, which is determining the rate of change, which is the inertial period. But during the inertial period, when the system frequencies decline, including your conventional group control, let's say from the generation, comes in and starts injecting active power. And that is what you see in the overlap in the blue, where the system frequency stops at a nadir and then transitions into a state where it slowly starts recovering, and that's your primary frequency control or frequency containment reserve, that concept. Once the frequency decline has been contained, in the next phase, which is the green trace, it's transitioning into the secondary frequency control zone, and then finally the system gets back to the steady state with either something that you call frequency restoration reserve or tertiary frequency control. In the technical brochure, in technical definitions, we have tried to give precise definitions for frequency containment, restoration reserves, and also something called fast frequency response. Fast frequency response and inertial response kind of share that same form of time scale, where it's really looking at less than 0.5 seconds. Do we want to inject before that point of time? Is there an active power injection that can come from the inverter-based resources? And we'll look at the definition further forward. So these 3 types of frequency control. The other important concept that is looked at when we look at frequency security as a whole is also the single largest in-feed. So we define what an SLI looks like. Why is it important? Because certain system operators around the world also are currently looking at operational strategies which basically maintain the SLI so that your system is never exposed to a single largest in-feed or out-feed loss, which will get you to rock-offs which are undesirable for your system. So what does that look like, and how will you define those? That has been taken into consideration. And also something that we wanted to address was the concept of synthetic inertia. Because that's a term that has been widely used in the industry, we wanted to kind of standardize what that might mean. What our technical brochure says is synthetic inertia is essentially a form of fast frequency response, or if you wanted to really bring in the concept of the fact that there is an inertia behind the inverter in this particular case where you emulate inertia from wind, we would like to introduce the term IBFFR or FFR, so inertia-based fast frequency response, because in its very core, there is still the concept of getting that kinetic energy, but then injecting the power to the system. So in a nutshell, all the various stages of frequency control are defined for the users upfront in the technical brochure. After the concept of inertia is established and the fact that operators around the world are looking at maintaining frequency security, and that may be from either maintaining or controlling the SLI could be from imposing critical inertia floors, or could be from imposing rock-off constraints. There is this inherent element of where my system is in terms of the inertia at this time to where it needs to be. So you're constantly trying to look at a number where it says, based on the number of generators that are online on my system, how much total system inertia is actually available, so that you can always kind of calibrate and maintain a good amount of inertia in your system. Now, having said that, not all utilities in the world are currently employing real-time monitoring of inertia, but many of them are. And in our technical brochure, we discuss some of the utilities who are looking at monitoring inertia in real time. Most of the utilities that we found out are looking at monitoring or estimating that system inertia based on the MVA aggregate method, which is basically SCADA based. All you need to know is the circuit breaker position of the various generators and their nameplate inertia, and they're estimating based on that what is the total kinetic energy available in the system. An example is shown on the screen from PinGrid, and there are multiple other grids in the world who have a similar kind of monitoring available. The other aspect is forecasting. Utilities who currently monitor the inertia based on the weighted average also look at forecasting the inertia in a couple of hours look forward, and one of such examples is ERCOT, who are currently doing that, and also the Nordics, as also shown on the screen. Now, when we come into the to the concept of inertia monitoring, forecasting, or even estimation, there are other methods that are currently available in the literature as well as in vendors. Now, where does the question come that why can we not rely on the estimates that we are currently finding using the methodology that most utilities are currently doing? That's the question that comes to mind. Why do we need to look at other inertia estimation technologies? So we have also handled that question and shown that the other techniques exist at times. If you have lots of inertia coming from behind the meter generation, or even behind the meter load or demand contributions, or in an environment where your system is no longer very strongly coupled, and if there are weak parts of the system or a non-uniform renewable penetration that's taking over the system, there might be inertial centers that are weakly coupled to each other. In that scenario, does the estimation that we just discussed, where we are MV averaging, does that work? Or if not, what other forms of estimation technologies exist? And I have kind of pointed them out in bullets. These are measurement-based techniques, and they usually are based on the measurement of frequency and active power. There are vendor solutions out there which have been discussed as well, in form of either intrusive techniques where you inject some sort of active power pulse, either by supercapacitors or some other form, and take those impulses from parts of your network to give you an estimation of inertia. There are others which are event-driven and purely based on post-processing data. There are some machine learning-based techniques which are all ambient data-based, so do not rely on large event-based techniques. And there are multiple different variants of how to estimate system inertia. This table basically has been included in the technical brochure to give a sort of understanding what capabilities exist in each of these types of inertia estimation techniques. What is the input data requirement? Whether or not a real-time estimation is possible, whether or not they estimate physical rotating inertia, or do they give you a regional estimate? Is it capable of providing forecasts, and whether or not do you need additional monitoring requirements to be installed in the system? So you can look at this at your own time, but sort of a overviewing picture of the various real-time inertia monitoring and estimation techniques that exist. With that in mind, then and I'm trying to capture the whole technical brochure so that the story flows in my head, but maybe it doesn't. So let me know what your thoughts are and if we are missing something here. But once we have established the definitions of frequency reserves and we have identified monitoring and estimation requirements around there, the next part was our chapter 3, which was purely a survey exercise. And in this survey, we basically approached all the utilities around the world and tried to ask them questions around what your current frequency control requirements are. Do you have fast frequency response in your system at the moment? Are you looking at minimum inertia levels? Is that a requirement that you have? What are your ideal system characteristics, and so on? I've presented some of the results here, and these are quite interesting just based on the responses that we got. For example, the inertia floor, although before we discuss the results, I must also add a caveat that, of course, it wasn't possible to provide a picture with all the utilities. We approached some 28, and maybe these results are more suited to the utilities that have slightly more urgent needs for renewable integration or targets and so on. So it should be taken with a pinch of salt. Having said that, the inertia floor requirement seems to be a majority of yes for most of the utilities that were approached, with some of them who do not see the requirement. What's quite interesting is to look at the fast frequency response solution that is currently out. And it seems that the utilities have something which they do not necessarily want to call fast frequency response, or currently maybe are looking at some other means of solving the problem in the inertial time frame. So there is a good percentage of utilities who answered no to having FFR provisions at the moment. And what was quite interesting is when we discuss mitigating measures, the idea is to bring in all the mitigating measures that are there under the sky, but there are utility specific ones, and which is the third pie, where a lot of them have other mitigating measures which are very network specific and so on. The other thing to highlight here is the graph that you see, which is basically the inertia in gigawatt second constant versus the total demand that is in the system. There are some large interconnects like ERCOT, which have very high demand, but you can see that the inertia kind of matches that. And that would hint to the idea that they are still serving majority of the demand, maybe using the inertial generation as sources. On the other side of the spectrum, when you look at the valley, systems like AirGrid, Manitoba Hydro, they are in just pure size, they are much, much smaller when you look at the demand, but then you can see the inertia and how it aligns with the rest of the networks that are shown here. And they are operating really at very reduced levels of both demand and inertia constant when just looking at it at a biggish level. And all of this is interesting just when you look at where the demand is coming from at the moment. And these are values of what is happening in the network at the moment. The other international experience that I wanted to capture was the procurement of frequency control reserve. Now, this is way more involved than what we can capture in one slide, and we'll discuss that again later on. But these were basically taken from the responses that we derived from the utilities. What we want to show on the pie chart here, that still in the world, the primary frequency response, or the FCR, is primarily derived from synchronous generation. So the inertia and FCR has a linear relationship still in parts of the world. But there are notably others. So for a majority of the utilities, synchronous generators are now complemented with wind and battery energy storage, which is the second largest pie pot there. And of course, for some of them, 7% wind. It depends on the generation mix, and we can mix and match. Now, of course, this pie chart will change based on whether it's a mandatory reliability imposed criterion, like let's say ONS in Brazil, or whether it's a market-based technology neutral frequency reserve procurement. And that is something that we will discuss moving forward. Point to take from this analysis is look at the different mixtures of where the primary frequency control or frequency containment reserves are coming from, including loads, wind, HVDC, and various combinations of those which are currently serving as solutions to various utilities in the world to support frequency security. The one point that I wrote at the bottom is also important because I know our technical brochure is looking at increased penetration of renewable resources, which are all inverter interfaced. And we are mentioning that we lose synchronous generators. It's important to also point out that losing synchronous generation or getting displaced does not only show in lack of inertia, it will also show in your system strength or grid strength, your fault current contribution, and there are multiple other impacts that are maybe loosely hinted at in our technical brochure, but the primary focus is inertia. But we do fully acknowledge that it's not just lost inertia. Okay, Marta, are we planning on carrying on to the next section or taking a break now?
If you feel like taking a short break now and we can continue in 5 minutes.
Yeah, that'll be good.
Perfect. So we'll do that. We'll kind of have a short break now and we'll be back in 5 minutes. Please don't go too far and come back in for the next part of the presentation. Thanks.
Okay, thank you. I appreciate everyone's patience, of course. Let's dive into the next three chapters within the technical brochure, which would discuss the challenges associated with increasing penetration capabilities and control strategies. So let's dive right into it. When we discuss challenges, of course, there are many, and I have put some of the examples here, and more can be looked into in the technical brochure. But let's discuss what some of them might look like. Of course, the one that is quite understood is the high rock-off rate of change, which means we require faster responding services, which brings into the question of fast frequency response services. The other thing is, with increased renewable generation, there is more intermittency, which inherently asks for more regulation. Also brings in concerns around power quality because of the sheer presence of increased power electronics in the network. Also brings in problems around challenges, I shouldn't say problems, of ramping reserves and what those ramping requirements are. When we discuss in the realm of inverter-based resources, all those ramping requirements actually have to be translated, either given in form of a policy requirement, or the vendors need some sort of understanding of what those requirements are, and the planner has to understand, based on future system studies, if what has been given ensures that they do have frequency security. Other interesting things based on the concept of renewable energy zones is, like, if you have wind-rich or solar-rich places, the concept of what happens during cloud covers, wind fronts, forecasting errors, that are all part of the high renewable penetration, and how do they impact the reliability of your network. So also, when we discuss protection, there are concepts around, you have to always guard against what your current frequency reserves are, what are the time constants, and then looking from there, what are your load reserves or other reserves when they are kicking in, what's your under frequency load shedding, and that will be tied into the sort of challenges. If the rock-off increases, you will hit those faster, so you have to try and prepare against those. Also, the concept of overfrequency. So how do we deal with that? Do we want to have a ramping product, or do we want to mandate, let's say, over-frequency generation trip or stuff like that? So there are overarching challenges in just the realm of stability. Then just a nod to the protection elements, like I was mentioning, when we talk about IVRs displacing synchronous generation, of course, the question comes about the system strength in the system. Also, the fault current contribution. When large synchronous machines are displaced by, let's say, a lot of small machines, is there a chance that the fault current that is currently available to detect faults is going to be much lower? So do you have to update the protection settings? And this is currently in place in utilities around the world who are revisiting the control operations. And that also includes large power swings when in low inertia systems that will directly impact your out-of-step tripping because of the size of the power swing. So how can you differentiate when it is caused by low inertia versus when it's actually a problem in the network? One other interesting point is around the negative sequence current injection, where traditionally inverter-based resources have not been mandated or asked to inject negative sequence. Then in presence of unbalanced faults, what does the impact look like? Is that a real challenge? Do we need to look into not only asking for negative sequence contribution, but how do we actually handle it in real time for planning and so on? The last point around the anti-islanding protection is quite common in the grids of Ireland, National Grid UK, as an example, where you have anti-islanding protection on distributed energy resources which are based on rock-off. So there are also programs which are looking at revising the settings based on most current rock-off constraints that are in the network. And that is inherently tied to the future penetration studies and in what you expect the rock offsetting to be, and then how can you differentiate when it's an actual islanding detection versus when it's just normal operation. And so the technical brochure also focuses a little bit on such protection challenges. Then once having identified the said challenges, the solution comes directly after that, right? So the solution is now going to come from all the different technologies that have been proposed, understood, and we are investigating at the moment for our requirements. Of course, synchronous generator in the top is a natural provider of synchronous inertia. And in terms of what it can provide, the traditional group governor response and so on. This table also shows the other options that are currently there in terms of loads, synchronous condensers, flywheels, HVDC interties, wind turbines, solar PV, and batteries. There are inherent specific technological capabilities associated with each one of them. And also the question, one is the trigger time. So when the FFR is supposed to detect the fault, what is it detecting it based on? Let's say, is it detecting rock off? Is it detecting based on frequency? What is the trigger? Then what is the time delay after the trigger? What is the performance requirement once it has been triggered, and whether or not we require a sustained response from them? And if we want a sustained response from them, which of these technologies can provide those, and what are the sizing requirements? Is that economical, and so on and so forth? And we get into that discussion. A little bit of that has been captured in this table, and more has been discussed in the chapter. So let's focus a little bit more on the fast frequency response product, because it is directly in the inertial time frame that we are kind of discussing. So FFR, like I had mentioned once before, there is a need to standardize what that means. And the definition that the technical brochure has come up with is just active power that is injected to or absorbed from the grid in response to changes in measured or observed frequency during the arresting phase. It will improve the frequency nadir or the initial rate of change of frequency. Now, having said that, what is unique in defining a fast frequency response is all these characteristics that have been pointed out. A fast frequency response product is not only required to respond fast. There are utility-specific definitions tied to what they think is the best solution. For example, the recovery time and when the recovery is allowed, how long is the volume and the duration of the response for, whether or not you would have a buffer, whether this should be symmetrical or asymmetrical, and individual definition of these characteristics is inherent to defining an FFR product, or even saying that a technology is capable or not. I seem to have lost the control, or have I not? No, I have not, sorry. So based on those various definitions, what I have shown on the screen is a comparison of what it looks like and how different it is from one utility to the other. So for example, in AirGrid, there is for the AirGrid system, there is an incentive for responding below 2 seconds. And there is an incentive up to 3 times. If you respond faster, there is an ability that you get paid more. Also for AirGrid, it's more of a single definition that can sustain from 2 to 10 seconds. As opposed to that, if you look at the Nordics approach, it's basically more of an envelope situation where you have 3 different definitions coming into the picture with 3 different thresholds for frequency where a different kind of FFR can come in. The same for, interestingly, for ERCOT and National Grid ESO. Want to point out that the requirements that are shown here are proposed for their future service definitions, not what they have at the moment. What has been widely accepted is fastest is not always the best. Your fast is defined based on your network requirements, and that's where these definitions vary so much. Fast frequency response can be dynamic, can be static or stepped, and at times it could be a combination of the two. For example, in Ireland, they have a definition for each. They can use a mix of each one of them, whereas some of the others, like ERCOT and Nordics, use static step responses from loads. AMO has a combination of those. It's important to mention the different types of fast frequency response services as well, because in your studies, these will directly impact the results, the answers that you're getting, and how you derive the policies and so on. So this kind of ties in quite well. And I know I'm rushing a little bit. I just want to make sure we have time at the end for a discussion. So if anything requires more clarification, we can always revisit at the end. With these various points in mind, let us transition directly to the last 3 chapters within the technical brochure, which will tell you what the utilities future system studies look like, and what are these services, where are they available in which utilities at this point of time, and what are the grid code policies around those. So the studies portion for future systems is really, really hard. Why? Because one, you have to determine, are you looking at long-term 5 to 10 year study period, or are you looking at more deterministic short-term, let's say, look forward 5-year kind of studies? And the approach varies from Europe to North America to Australia. It's not universally known, but more or less they're always determined by what the renewable energy targets are that are directly coming from either the regulators or the government itself. So they can be static, dynamic, or quasi-static studies, where you determine what is the demand projection, the capacity projection, and what sort of SFR or other sort of frequency reserves would exist. And based on those studies, then you would determine whether there's a shortfall that you may have to prepare for right now, or so on and so forth. This is handled in Europe quite differently, and it's based on a concept of future scenarios. They're dedicated let's say, visions of what the future may look like, where you're simultaneously studying, let's say, high distributed generation versus a majority of, let's say, very centralized, large renewable integration. And each of those scenarios is studied in parallel, and to try and understand, okay, we are prepared for maybe solutions which are optimal across the board, or maybe suboptimal, but serving one or the other objective. When we mention future system studies, it's very important then we delve into the question of modeling. And when we discuss models, we are talking about generation, demand, and network. So one thing which is already quite widely discussed in the community at the moment is, in the planning time frame, are we discussing RMS simulations, quasi-static simulations when batteries and state of charges kind of conversations are coming in, or are we discussing EMT level detailed simulations? Again, the answer lies in the network requirements that you currently have. What I tried to highlight here, within generation, again, there is the division between what is the synchronous generation, large renewable, distributed energy resources, which are aggregated at the bulk power system level. Is that aggregated model enough? If not, what kind of models are available in the various in the literature that can be used, and storage models. When we discuss demands, again, very difficult behind the meter projections of static and dynamic loads, and also whether or not you have demand side management. How are they aggregated? What sort of dynamics or controls do you need to capture in your aggregate representations? And lastly, if the network has non-wire solutions within them, like power flow controllers or stuff like that, how are they included into your future system study? And of course, overarching, because it's all inverter-based resources, the control philosophy and the protection would be vitally important. Are the protection settings and control configurations grid following versus grid parallel? Which parts of the network they are connected to? And directly, what are the control variables themselves? Are the instability that you see, is it because of that or something else? So with that, I have mentioned two examples of system studies. The first is done from AMO, which is included in one of our chapters, where they are trying to determine the secure operating level of inertia. The steps are outlined for this particular study that they do. They start with the identification of the most relevant contingency. When islanded, the secure operating level of inertia is relevant for each of the islands to support themselves if the situation were to occur. So the loss of largest generating system or load in that island, you assess what the relationship between inertia levels and required frequency containment reserve is, and then directly compare it in step 3 to the available quantity of FCR, and from that intersection point, identify what is the secure level of operation reserve. One second. Yeah. So that's the kind of study that they do to identify what's the requirements for reserves. Few interesting results that have been shared. If you look into the figure on your left, for the contingency size of 300 megawatt, basically what was found out that a mix of FFR and fast frequency containment services, FCAS, actually affords a reduction in the inertia requirements to maintain acceptable frequency, and that's quite interesting. So if you see for the low inertia curve, which is the blue, for the same amount of FFR, you're getting a much higher percentage reduction in inertia requirement, and vice versa, that proceeds. What's also interesting to see is the figure on your left, where we are looking at 3 different levels of inertia. And if we were to maintain a 1 Hertz per second rock-off constraint in the system, what this figure shows that for a low inertia system, which is more nimble and agile, the same percentage of FFR or FCAS will help, a much lower percentage of FCAS will help you maintain the rock-off constraint, as opposed to if you had a higher inertia system. So this is quite interesting. So you get more buck for every megawatt of FFR that you are using in your system when it's more nimble and agile. And that's quite interesting in itself. Another study that we kind of discussed would be how ERCOT quantifies their frequency containment reserve. So their ideology comes from, we are looking at a generator trip, and their largest contingency is 2.7 gigawatt generation loss. Looking at what the UFLS threshold is, where their RRS or the responsive reserve services come in, their resources, LR as they are called, they step in at 59.7 Hertz. So in the past, ERCOT used to procure 2.8 gigawatts of frequency containment reserves. And they're studied as we look into various inertia states in the future, does that number change or not? So the results are shown right here. On the top, the study basically is looking at a number of time domain simulations that they did, where they're only concerned about the primary frequency response requirements. And basically what was found is, as you look at lower inertia hours, the amount of PFR requirement goes high, which is kind of okay. We sort of understand that. And they take all those time domain simulations and try and create a relationship using a regression. That also is shown on the heat map on the top, where the RRS requirement is shown. So during the low inertia periods, let's say the winter mornings, the requirement is quite high, the RRS requirement, whereas the high inertia periods, of course, the blue, it's not as high. The second part is then, if we were to substitute, or not substitute, complement the primary frequency response with a service like LR, which could be thought of as an FFR kind of service, very similar to the fast FCAS in AMO's case. For every 1 megawatt of PFR that you can substitute, how much load reserve do you need? That is actually shown by a ratio that they call the equivalency ratio, and basically goes, as your inertia reduces, of course, your rock-off is high, you need more LR services during those times to make sure that you don't hit those points. And that's again shown by the ratios that you need higher equivalency ratios in low inertia periods in through the year in ERCOT versus the high inertia periods. Now, based on that understanding, ERCOT determined a critical inertia floor where basically allowing for the 0.5-second delay of these load resources to jump in, they wanted to identify how much reserves were required to when the system frequency transitions from 59.7 to 59.3, which is their UFLS settings. And the critical inertia was actually determined to be 94 gigawatt seconds. What you see on the top is the study for different inertia levels, where the two red dotted lines are the two frequency levels where the LR resources actually trigger to their UFLS. And they're trying to make sure that 0.5 second during that time, they never hit the UFLS settings. And that has been shown in the lower portion of the graph, where you see to get inertia corresponding to FFR, where you can get to a point within 0.5 seconds is actually 94 gigawatt seconds, and that turned out to be the critical inertia floor for ERCOT. The thing that should be pointed out is that in their current system, 130 gigawatt seconds is the lowest inertia experienced to date. So they are kind of well above the security margin that has been determined, and this has not been changed yet, and they do not see a requirement to change it as of yet. So that's another example of a study that was done to derive that. So let's directly transition from then the studies, come up with requirements for, let's say, fast FCAS or FFR and so on. What are the market mechanisms available, or does there need to be a market mechanism available to then derive that service, or are we going to call that service inertia based or so on? Let me just retrace my path a little bit. Yeah. So the next question that we tackle is if at all inertia needs to be provided as an ancillary service, because synchronous generation has been in the system in the past and has been providing inertia for free. So is there a need now that we need more and more inertia on the system because of increased IBR penetration, and we understand the challenges, do they need to be provided some additional benefits or for providing that service? So EirGrid and Sony are one of the prime examples who came up with synchronous inertial response as a service, as a product. And it is quite interesting, and this was implemented as part of their DS3 system services program. What the synchronous inertial response service basically means is that it's providing you a tariff for the kinetic energy that's provided by the machine. But what's very interesting to see here is the surf factor, where surf factor basically is the ratio of the stored kinetic energy to the minimum generation. And this is to ensure that it incentivizes the synchronous generation within the system to produce less power in real time and maintain a min generation, but then they are getting rewarded for providing synchronous inertia. The value of SERF lies between 15 to 45. Basically, it's capped at 45. So if the minimum generation is 0 or less, you're getting the full amount. But it avoids generation, synchronous generation, from producing more and more in that more and more energy in the energy market, because in that sense, then you won't get a tariff for SIR. There are a lot of us maybe from EirGrid who know much more on this particular product, but at a high level, that's an incentive-based product that serves synchronous inertia. One other notable thing that we wanted to discuss in the technical brochure is the stability pathfinder, where NGESO went a different direction, where instead of defining a separate synchronous inertial response, they came up with a stability product which bundles voltage and frequency requirements together. What are the key performance criteria? And I've kind of highlighted in green right at the bottom. So on top of inertia, they're asking for short circuit contribution, reactive current injection, and ride-through performance. So this is usually one very important thing to note here is for stability pathfinder, existing assets and new build need to have 0 megawatt export. So that's a pre-qualification requirement. So only synchronous compensators or synchronous generators, they could participate. And as of last year, I think 12 contracts were provided as part of this service, which is also one of the flagship ones. So we are quite at the end of what we were to discuss here. So we discussed if Inertia could be provided as a service. Lastly, we wanted to also look at what are the existing grid codes and policies in place for, like, let's say, definition of minimum inertia level calculation methodology, and the frequency, fast frequency response requirements. And the answers were quite interesting to look at because different approaches were followed to deliver the same function. For example, in AirGrid, they came up with a new agnostic service, which is like technology neutral, but has their own way. For ERCOT, they are kind of sticking to specific load and battery energy sources as a service at the moment. Nordics also use a load-only service at the moment. AMO just extended their existing FCAS requirements and called it FFR plus FCAS, and kind of complement each other. So one of the other interesting things was many of them said who don't have a fast frequency response requirement at the moment have other mitigation measures. And that's interesting. And we'd like to hear more, hopefully in like a future working group, what the other mitigation measures are that have not been captured on top of, let's say, the minimum inertia calculation and the past frequency or frequency containment reserve requirements. So that is, I think, in a nutshell, what I had in terms of the chapters. So let me quickly maybe spend 2 more minutes to finally boil everything down to final concluding remarks. As part of the work done in the technical brochure, we discussed and we identified inertia is a growing concern for utilities, but a lot of utilities have come forward and there are different solutions that are currently in place, and study methodologies that have been outlined, lots of public information that is available, and there's a lot that we are learning from them. Till now, studies are found to be the common aspect which determines inertia shortfall or reserve adequacy requirements for future studies, and for most times these are dynamic studies which take into consideration all the different needs. So a further sidebar from there would be the modeling requirements and what are we missing in those future studies, what else do we need to do in the scenario selection and scenarios that we are building for the future, and so on and so forth. Lastly, because it's an inverter-based generation heavy environment, we need to discuss voltage alongside frequency. So it's a combination of low inertia as well as like low system strength. So a stability product probably moving forward is something that we will discuss more and more into our conversation. And lastly, we need to discuss a few other things, and I would just highlight the middle one, which is control. As we move towards very high inverter-based generation, we know we'd be looking at modeling challenges and also the inverter capabilities for handling weak grid kind of scenarios, because we are aware that there are challenges when you try to inject the active power in form of your FFR into a weak grid, because control philosophies will make it difficult. There are PLL instabilities that might come into picture. So there is a dedicated chapter discussing those controls as well, and something that I haven't included in our talk today, but that's also very, very important. So I think with that, I would probably stop. That's all I had. Marta, do you want to?
Thank you very much, Fabia, for this very, very interesting and detailed presentation on the work of the working group. We have quite a few questions. We have very little time left, but I will just kind of start with the first question. What is the status of the working group, and when can we expect to see the technical brochure? We're all looking forward to put our hands into it.
That's a great question. So we are at the final stage, and expect to hand our technical brochure to the study committee for review by end of March. So we are at the final stages of review and editing at the moment.
Thank you. And we have another question here. Papilla, do you envision a future where a big portion of the grid is operated in DC? I'm not sure if this is very much related to the working group, but it's an interesting question anyway.
Yes, of course. Yeah, so I'm trying to see how we answered that. Of course, the big answer is yes. And I think we've all seen a lot of that already, either with current plans or the new interconnection queues. But let me try and also draw the picture internationally on top of what we have in Europe and to what we may foresee in North America, because there's a lot of conversations around this. In general, the advantages we get with more interconnected system and the advantages of having the ability to share frequency reserves with neighbors is an advantage, and doing that over DC provides obvious advantages in multiple ways. It has not been taken up as extensively, and there are multiple reasons, of course, because when you come to decisions like those, you're looking at long-term expansion planning. And if your vision of the future, based on the various solutions that do exist, because that's not the only solution, there are other solutions as far as interconnection is concerned. If that comes out to be something that's more valuable to you, then yes. And in general, there is a bigger uptake to DC. I don't know if you'd like to add something to that, Marta.
No, I think that you covered it very well. I think that we'll go to the next question. We have quite a few, so we'll try to get as many as possible. So Mustafa Bakhtar is asking about converter-based generation can provide synthetic inertia, but it doesn't provide synchronous torque. How can the scarcity be compensated? What technologies are out there? I think that's what he's asking about for synchronous torque rather than synthetic inertia.
Yeah, that's an interesting one, and also something that I think we loosely touch on, because the concept of synchronous torque directly ties in with the concept of dynamic coupling between different systems. So short answer would be some utilities are already looking at solutions like synchronous condensers, or like non-inverter based flywheels that can actually provide some help with that. But then I guess there are other means of looking at the lack of synchronous torque. Like, what is it actually causing, and why would you want to supplement it? And it's again very specific to the areas of the network where you may see regrid kind of issues and how that can be handled. Not necessarily using synchronous inertia, but like as we have seen, some utilities like to maintain critical inertia floors across the system. Maybe you could foresee a world where you're looking at regional floors with pockets of inertia that are maintained, so that some amount of synchronous torque or dynamic coupling is still restored. Yeah.
Thank you very much, Pia. And I think I'm going to bundle two questions, and we'll just finish with that. Abel is saying, thanks for the research. I just had a query related to the ability of electric vehicles. Is vehicle-to-grid concept feasible on a long-term basis? And then the next question comes from Thomas O'Sullivan in the same kind of topic of demand response. Have you considered flexible electrode boilers? Oh, it's gone. Here we are. Offset foil fuser fuels across industry, reduce curtailment, provide 0.2 seconds pour, maximum use of local grid. So the two questions are very much interrelated. It's about the use of demand for providing these fast frequency response services. So if you could comment on that, please.
Sure. That's a great point as well. So we haven't explicitly mentioned flexible electrode boilers, so thanks for that comment, Tomas. I think I'm going to take that down, and we will include that in the technology section. But in a broader sense, like Marta is saying, because it's sort of a demand side service, in cases like air-grid where it's technology agnostic, it would obviously be considered in the same way as long as the performance requirements are satisfied, which what you're saying is, yes, it is. So if they produce that they can provide the required performance, then absolutely yes. And we will actually call flexible electrode boilers out in the technology section. We haven't yet done that. Now, coming back to the first part of the question, which was around hybrid electric vehicles, it's I think a difficult one, and I know many of you may have a different viewpoint to mine. I think this is also related to the point of behind the meter distributed energy resource or something like that, right? These electric vehicles, one on top of not necessarily, when we are trying to aggregate, they also provide on top of the temporal variation, they provide a spatial element to it, which brings in more uncertainty. So I would just think that the aggregate models or the product as a whole in megawatt will be a little bit more difficult to define or to include. So I would think that it's a little nascent at this stage, but that may change with increased penetration where it becomes more apparent where the charging stations are. These are the modes. So a lot of work needs to be done on the mathematical modeling part of it to really understand how we can define it into a condensed product. That would be my thought.
Thank you very much. We're just kind of close to finishing the time. So I think I'm just going to thank you, Papilla, for this excellent presentation. Everybody I'm sure that they will agree that has been very detailed and very insightful. And it's an area of increasing interest for the industry, for system operators. So thank you very much. I know that you have put a huge effort in preparing this presentation. So thank you from myself and from the point of view of CIGRE Ireland National Committee. I also want to thank...
My pleasure.
Thanks. I also want to thank Jason Nocton and Valentin Rigoni, who are there in the background. They've been kind of making sure that this event was running smoothly, and they also put a huge amount of effort in the organization of the event. So guys, thank you very much for all your effort and your support. And also want to thank CIGRE Ireland National Committee for supporting these events. And finally, I want to thank everybody in the audience for listening, for your attention, for your support to CIGRE, and for the very interesting questions that have been posed. And we had a great discussion today. So thank you very much, everybody. We're going to leave it here. Thanks for listening and keep safe.